Welcome to our second activity on the category of vector spaces. We are going to address two natural questions about linear maps. First, let E and F be two vector spaces, and let phi be a linear function from E to F. Let us assume, moreover, that phi is a bijection, so phi has an inverse map from F to E, and we wish to know if phi inverse is also linear. Let me remind you of a characterization of linearity from our first lecture. We learned that a function phi from E to F is linear if and only if, for any two vectors v and w in E, and for any scalar lambda, phi of lambda v plus w equals to lambda phi of v plus phi of w. Now, the inverse of phi goes from F to E, so to prove that it is linear, I will take two arbitrary vectors x and y in F and a scalar lambda. Since phi is a bijection, it is surjective, and thus there exist two vectors u and v in E such that phi of u is x and phi of v is y. We now follow the guideline given by the characterization of linearity. The inverse of phi can be calculated at lambda x plus y by noticing that we can replace x by phi of u and y by phi of v, and then by observing that since phi is linear, lambda phi of u plus phi of v equals to phi of lambda u plus v. But then you observe that we apply phi inverse to phi of something. By characterization or property definition really of a bijection, we conclude that the inverse of phi applied to lambda x plus y is really equal to lambda u plus v, which is lambda phi inverse of x plus phi inverse of y, since phi of u is x, therefore phi inverse of x is u, and similarly phi inverse of y is v. If you look where we started and where we ended up, you see that we have proven that the inverse of phi applied to lambda x plus y is equal to lambda, the inverse of phi applied to x, plus the inverse of phi applied to y. Since x and y were arbitrary vectors in F, and lambda was an arbitrary scalar, we have proven that the inverse of phi is indeed a linear map from F to E. This is actually a general phenomenon for algebraic structures. For instance, you can prove that a morphism from a group to another, which is also a bijection, has an inverse map which is itself a morphism. However, this is not true in every category. You will learn in topology, for instance, that there are bijective continuous maps whose inverse are not continuous. For our purpose, this removes a potential confusion and also provides us with a new tool to prove that a map is linear. Our second problem is a little bit subtle. It asks the following question: must an additive function be linear? To answer these questions simply, I will use complex numbers. But we will see in this exercise a few subtle points beyond the original question. Let me define a map which to a complex number of the form a plus ib maps the complex number b plus ia, that is, flips the real and imaginary part. I'm going to first ask if this map is linear from C to C. We saw in our first activity how to prove that a map is in fact not linear, and this is exactly what happens here. We do a couple of simple calculations. Phi of 1 is I by construction, and phi of I is 1 by construction. However, since I times 1 is I, we should have, if phi is linear, that phi of I is I times phi of 1. Yet I times phi of 1 is I squared, which is minus 1. So we see that since 1 is not minus 1, phi of y is not equal to I times phi 1, and phi cannot be linear. This, however, assumed that we were working with the complex numbers as the scalar field, as the question asked. Since C is a field, it is a vector space over itself, and we can see immediately that phi is not a linear map here. But it is an additive map. That is, if you take any two vectors in C, that is two complex numbers, and you add them up, and apply phi to that sum, well, you get the same answer as if you applied phi to each term and then add them up. The little calculation is listed here. So while phi is not linear from C to C as a vector space over itself, it is, in fact, additive. So there are additive maps out there that are not linear. There is another point of subtlety that I wish to conclude this activity with. You see, here we look at C as a field and therefore a vector space over itself. But C is also a vector space over the real numbers. Simply multiply a complex number by a real number. That's the external multiplication, and we keep the addition unchanged. It is easily checked that we have a vector space, which is in fact simply R squared. So we could ask, is phi linear for that vector space structure, where the scalar field is just limited to the real numbers? And it's a simple calculation to see that the missing property, that is, phi is a morphism for the external or scalar multiplication, indeed does hold when we restrict ourselves to real numbers. What it means is that phi is actually linear from C to C when considered as a map from a real vector space to a real vector space. But it is not linear as a map that goes from a complex vector space C to the complex vector space C. It is, however, additive either way. So it is important to remember that being a vector space or being a linear map does depend in particular on the choice of the scalar field. I will leave you to ponder on an interesting question. Could I find an additive map from R to R, where R is seen as a vector field, vector space over itself, which is additive but not linear? Is there an additive nonlinear function from R to R as a vector space over itself? And the short answer is, it depends, but if you assume the axiom of choice, then yes, there are such maps. It is a significantly more involved problem than the one we just saw here with the complex numbers. This concludes our activity.